So now we're looking at continuity. So we already talked about one-sided limits in the last section. We had to make sure if the limit exists, it had to be, the left side limit and the right side limit had to go to the same thing. So continuity is using that one-sided limits, and then they're adding one more piece into it. So if we're looking at this example, f of x is x minus 1 if x is less than 0, x plus 1 if x is greater than or equal to 0. First thing we want to look at is the left hand and the right hand limits. So the left hand is when it's less than 0. So if I go getting closer and closer to 0, you just plug in 0 into this, we get negative 1. The right hand is at x plus 1. So as I get closer and closer to 0, again, just substitute that in, I get a positive 1. So therefore, the limit does not exist. It doesn't exist because the left-hand limit and the right-hand limit go to two different numbers. Continuous function, we're still going to look at that left-hand and right-hand limit, but we're going to have to add one more piece in there. That all three of these things must be true for it to be continuous. The limit has to exist, which means the left and the right hand side has to be the exact same. The function has to exist. So remember, that piece wasn't necessary when we were talking about limits. It didn't matter if the function existed. It just mattered if the left and the right hand limits existed. But now it does for continuous. The function has to exist. And then this third piece is the limit has to equal the function at whatever point we're looking at. So I have up here, we can have no holes, jumps, or vertical asymptotes. Anything that you'd have to pick up your pencil for if you're graphing it to go to the next point, it's not going to be continuous there. You should be able to do it in one flow. So the limit must exist, the function must exist, and the limit has to be equal to the function. So those are the three pieces that we need for continuity. So here I have a picture for you, and we're going to identify all the discontinuities, and then we're going to talk about what kind they are. So in this course, we're not going to get too much into removable and non-removable discontinuities, but it's important to know whether there's a big jump there or it's just a little hole that you have to jump over. So our first discontinuity is at negative 3. The limit doesn't exist. The function exists. The limit doesn't exist, so therefore it's not continuous. There's a big jump there. Our next discontinuity is at negative 1. So this dashed line, when you see that up and down, that's really trying to show you that there's a vertical asymptote there. So if there's a vertical asymptote, the function doesn't exist. The limit is going to positive infinity, which again is not a real number, so that's not really helpful. So we have a vertical asymptote, therefore it's not continuous. And then the last place it's not continuous is over here at 2. So the limit exists, right? The limit exists. It's both going to negative 0.5. The function exists at 2. It's at negative 1. But the limit doesn't equal the function. So therefore we have a hole, which is also called a removable discontinuity. So I have a hole there, so therefore it is not continuous. Alright, so we're going to look at equations and determine whether there's discontinuities. And really this is completely related to the domain. If there's something that's not in the domain, then it can't be continuous at that point. So for our first example, we just have a nice polynomial. It's a polynomial. I can evaluate a polynomial for anything I want, so therefore I don't have any problem spots. And remember, we had to worry about division by 0, and we had to worry about imaginary numbers. Well, there's no square root and there's no rational expression, so therefore it's continuous everywhere. The second one, we have 2 over x squared plus 1. So I'd have to worry about the denominator being 0. Well, what can make x squared plus 1 equal 0? It can't. There's nothing that makes that 0. You could subtract the the 1 over, and you get x squared equals negative 1, which doesn't work, because when you take the square root, you get imaginary. So there's nothing that actually makes that thing 0. So therefore, it's continuous for all x. Number 3, on the other hand, we do have a denominator that's factorable. X squared minus 1, we can set that equal to 0. So that factors to x minus 1 and x plus 1. And when you set each of those equal to 0, we get 1 and negative 1. So therefore, I have discontinuities at 1 and negative 1. And they don't simplify away. So those are actually asymptotes. We have vertical asymptotes at 1 and negative 1. Number 4, we're back to a piecewise function. So we have, the function is x if x is less than or equal to 1, and it's 1 if x is greater than 1. So the only thing we have to worry about is that point 1, because we know that x, that's just a straight line, that's a continuous function. 2x minus 1, again, another straight line, that's a continuous function. So the only thing that is going to give us a problem is when it jumps from one function to the other. So if I plug in 1 to the first one, I get 1. And when I plug in 1 to the second one, I get 2 times 1 is 2 minus 1 is also 1. So therefore, because I get the same thing for the limits and then the function value is the same, this is going to be continuous at 1. So this number 4 is continuous everywhere. Alright, number 5, I have x squared minus 3x plus 2 over x squared minus 2x. So first thing is, what makes the denominator 0? Because we know that's not in our domain, so it can't be continuous there. So we take the domain and factor it. So x squared minus 2x equals 0. Factor out the x, and then set each one equal to 0. So we get 0 and 2 are the places where it's discontinuous. And we can talk about what kind of discontinuity is a little bit, because when we get into graphing functions later, we're really going to want to know. So I factored it. So we had that x squared minus 3x plus 2 factors to x minus 1 times x minus 2. So this x minus 2 on top and the bottom simplify, and I get x minus 1 over x. So you can see when we simplify it, we remove that other problem spot, so it's called a removable discontinuity. And when you have a removable discontinuity, that's where you get a hole in your graph. The 0 can't simplify away, so that's where I'm going to wind up with a vertical asymptote. So I plotted out the graph for you. And it's a little bit deceiving because you don't see where the hole is, but there is actually a hole at 2. It should look like that, but the software won't graph that for me. And I also noted that you see that this thing levels off. In the last section we talked about horizontal asymptotes. So this has a horizontal asymptote at y equals 1. Go back to the original, and you see the greatest coefficient, or greatest degree is 2. And you look at those coefficients, you just get 1 over 1, which is 1. So we can see where that horizontal asymptote comes in. And then the last piece here is I want to find a k to make sure that this function is continuous. So again, the only problem spot I'm going to have is where it jumps from one function to the other, because I have a polynomial and a polynomial. So what I need to do is make sure this at 1 is equal to this at 1. So when you plug in 1 to the first one, you get 1 plus 2 is 3. So 3 has to equal k, and again I'm plugging in 1, so 3 has to equal k times 1 squared. Well, 1 squared is just 1, so in order to make this a continuous function, k has to equal 3.